There are supermassive black holes. There are ultramassive black holes. How large can these strange objects grow? Well, there could be something even bigger than ultramassive, stupendously large black holes, according to the latest research. Such hypothetical black holes, larger than 100 billion times the mass of the Sun, have been explored in the new paper which names them SLABs, an acronym that stands for stupendously large black holes. We already know that black holes exist over a vast range of masses, with a supermassive black hole of 4 million solar masses residing at the center of our own galaxy, explained astronomer Bernard Carr of Queen Mary University London. Whilst there isn't currently evidence for the existence of SLABs, it's conceivable that they could exist and they might also reside outside galaxies in intergalactic space, with interesting observational consequences. Black holes have only a few somewhat broad mass categories. There are stellar mass black holes. Those are black holes that are around the mass of a star, up to around 100 solar masses. The next category up is intermediate mass black holes, and how large they get seems to depend on who you talk to. Some say 1,000 solar masses, some say 100,000, and others say 1 million. Whatever the upper limit is, these seem to be pretty rare. Supermassive black holes SMBHs are much larger, on the order of millions to billions of solar masses. These include the SMBH at the heart of the Milky Way, Sagittarius A*, at 4 million solar masses, and the most photogenic SMBH in the universe, an 87*, at 6.5 billion solar masses. The chunkiest black holes we've detected are ultramassive, more than 10 billion but less than 100 billion solar masses. These include an absolute beast clocking in at 40 billion solar masses in the center of a galaxy named Goldberg 15A. However, surprisingly, the idea of SLABs has largely been neglected until now, Carr said. We've proposed options for how these SLABs might form, and hope that our work will begin to motivate discussions amongst the community. The thing is, scientists don't quite know how really big black holes form and grow. One possibility is that they form in their host galaxy, then grow bigger and bigger by slurping up a whole lot of stars and gas and dust, and collisions with other black holes when galaxies merge. This model has an upper limit of around 50 billion solar masses. That's the limit at which the object's prodigious mass would require an accretion disk so massive it would fragment under its own gravity. But there's also a significant problem. Supermassive black holes have been found in the early universe at masses too high to have grown by this relatively slow process in the time since the Big Bang. Another possibility is something called primordial black holes, first proposed in 1966. The theory goes that the varying density of the early universe could have produced pockets so dense they collapsed into black holes. These would not be subject to the size constraints of black holes from collapsed stars, and could be extremely small or, well, stupendously large. The extremely small ones, if they ever existed, would probably have evaporated due to Hawking radiation by now. But the much larger ones could have survived. So, based on the primordial black hole model, the team calculated exactly how stupendously large these black holes could be, between 100 billion and 1 quintillion, that's 18 zeros, solar masses. The purpose of the paper, the researchers said, was to consider the effect of such black holes on the space around them. We may not be able to see SLABs directly. Black holes that aren't accreting material are invisible, since light cannot escape their gravity, but massive invisible objects can still be detected based on the way space around them behaves. Gravity, for instance, curves space-time, which causes the light traveling through those regions to also follow the curved path. This is called a gravitational lens, and the effect could be used to detect SLABs in intergalactic space, the team said. The huge objects also would have implications for the detection of dark matter, the invisible mass that's injecting way more gravity into the universe than there should be, based on what we can actually directly detect. One hypothetical dark matter candidate, weakly interacting massive particles WIMPs, would accumulate in the region around a SLAB due to the immense gravity, in such concentrations that they would collide with and annihilate each other, creating a gamma radiation halo. And primordial black holes are themselves a dark matter candidate, too. SLABs themselves could not provide the dark matter, Carr said. But if they exist at all, it would have important implications for the early universe and would make it plausible that lighter primordial black holes might do so. Also, We couldn't resist calculating the size of a 1 quintillion solar mass black hole. The event horizon would end up over 620,000 light-years across. Stupendous. The team's research has been published in the monthly notices of the Royal Astronomical Society.